Okay, deformations. We have an IHSM X, and we give ourselves a Lagrangian fibration, and the ultimate goal is to understand where in the space of deformations of X this Lagrangian fibration evolves along. Okay, so we have a couple of deformation problems associated with this situation, so associated deformation problems was, so you take, first of all, you can consider F, then you can consider L, which is the F upper star of something so from B. You can take lowercase l, which is C1 of capital L, and my notation F was a general fiber of F, therefore a Lagrangian variety. The variety with a Lagrangian embedding X. And then we had the base of the universal deformation of X, and inside of this you have the subspaces def X comma F, which is the one that we're ultimately interested in. Here is def of X comma capital F, that means that the fiber deforms along, but maybe not the vibration. Then there is def of X comma L. Actually counted this in the Sophia code. And then there is the locus where the class L deforms along. That's also known as the Hodge locus. These are four subspaces in this space here. So recall this here is smooth of dimension equal to H11 of X for IHSMs. And now we're going to study these four subspaces. And let me maybe start with the obvious inclusions. So maybe, well, I want it to be here because I'm going to keep that picture here. So let me see who is obviously included in. So if I have def X comma F, well, if the if the vibration persists, then the fiber persists. So I have def X comma F. What else? If the vibration exists, then the line bundle persists, right? Because I can just keep on pulling back from the base. So this included in def X L. And if the line bundle persists, then its first term class remains of Hodge type. So this is included in the Hodge locus of L. I think for the moment that's all we know. Then there's a result which most of you know. I think we also used it explicitly, which is the local Torelli theorem by Bouguer. That's the following. So if I put dx in the following space, that's S in the projectivization of H2 of XC. Now maybe I need some more space. Oh, that's it. Okay. So I take the projective space of lines in H2XC, and I take a line represented by a vector S, and I want Q of S to be 0, and I want Q of S, S bar to be positive. That's the period domain for the Hodge structures that come with such an irreducible holomorphic symplectic manifold. And then we have then the local period map P from def X to this period domain dx. So how does this work? You take an element t inside here. Maybe so you have the universal family. It's curly x over fx. There was a special point, the fiber over this special point was x. So I sent t to, well, I have to go to a line here in h2 of xc. So I take the h2 0 of xt, which is on a line in h2 of curly xt comma c. But because we're in the world of germs, these germs are locally contractible. I have a unique way by parallel transport to identify this with h2 of xc. So I indeed end up in here. All right, theorem needs a statement. Local period map P is an open embedding. So you should think of this def x as or you can think of this def x as a small open sub in the period domain dx. And corollary is that we can describe the Hodge locus. The Hodge locus of L is just def x intersected with L perp.
Will you raise the board 7.6 centimeters?
In dx. Okay. So dx lives in a projective space. I take a hyperplane and I intersect this small ball with the hyperplane. So in particular, Hodge L is a smooth hyperplane in fx. All right, so this clarifies at least how this looks like. Any questions? Next statement would be a comparison of these two here. That is a theorem due to Hodge for IHSMs. I think it's due to the linear for K3 surfaces that says that the depth x comma L is smooth of codimension 1. So it's an unobstructedness result for the transformations of the pair x comma L. In particular, def x comma L is equal to Hodge of L, which where is the oh, there. Okay, which I think is not. Let's see. Which is not that much of a surprise. I think that along the Hodge locus, along the Hodge locus, by Lefschetz 1-1 theorem, the class is 1-1 and integral, so you get at each point a line muscle anyway. But all of them fit together, and that's this unobstructedness result for the two for def XL. So it means that these two here are equal by Halbrecht.
Can I ask a question?
Yeah, please.
So the def X we regard it as a formal scheme or like a net? What type of thing?
Yeah, def X. So in some sense we're better off than in Sophia's lectures because we work over complex numbers, and there you have things which are not algebraic. So this is actually a complex space. But I mean, to state it properly, all these results about maps and so on have to be stated in the category of germs of complex spaces, because well. Yeah, for example, I have this X over def X, so suppose I choose a representative of this, and I got this curly X over there. And then by deformation theory, over this subspace, I get a universal line bundle, but maybe I have to shrink the representative to make this statement true. And no, you should read all statements in the category of germs of complex spaces. So in some sense, if the relation between formal schemes and formal power series rings is the same as germs of complex spaces and convergent power series. The fact that we have convergence. Okay. So this is oh yeah, sure. So now I'd like to get to this def X, F. There is a theorem in the early 90s, actually, so it's 30 years old. So let Y in X be a Lagrangian subvariety. So it's a Lagrangian submanifold. So Y is smooth, X is, again, irreducible holomorphic symplectic manifold. Then def X, comma Y is unobstructed, so it's smooth, of codimension. So the codimension of def X, comma Y inside def X is equal to the rank of the restriction map in second homology. So I take H2 of X, I restrict to the submanifold H2 of Y, take the rank of it, and that's the codimension. So coming back to your question, this something I should add is the smoothness result is also only in the sense of germs. You know it in the point 0, and then of course if a space is smooth in one point, it's smooth in the neighborhood, but we don't know how big this neighborhood is. So all this smoothness is up to shrinking or represented. That's usually fine. Okay, so Lagrangian submanifold deformations of the pair are unobstructed. You can compute the codimension of this space as the rank of the restriction. You can say it more precisely. you put, say, V as the kernel of this restriction map, so kernel of H2x to H2y. Then def xy is a Hodge locus, and it's the Hodge locus. This was a Hodge locus of one class, L here. This is the Hodge locus of many classes, all the classes in V perf.
Sorry, but maybe this is a good point. That's what the clarification question I had. So when you were Hodge up there, you just meant yeah, the top one, or the bottom right, top one. You meant those are the guys where L remains a Hodge class. Mm-hmm. Okay, so it's dependent on L, but okay, I see.
Yeah.
I see.
Absolutely.
Okay, now we're going. Thank you.
Okay, so different index, different space.
And now we're different.
Okay, so I want all the classes to be perf to remain Hodge. Let's check for sanity that they were Hodge in the first place. So here, of course, I mean, Y is Lagrangian, and therefore the symplectic form restricts to 0. Symplectic form restricts to 0. Therefore, the whole transcendental lattice restricts to 0. And therefore, the perf of this is contained in the perf of the transcendental lattice, which is the cargo. So it's fine. All of them are Hodge classes. Okay. I don't look at you and I hear no complaints. All right, so here is a lemma by Matsushita, which gives the next comparison. Matsushita's lemma says that if let f, that's notation, be as above, so above on the board are erased, which means we have f the Lagrangian fibration, L the line bundle, little l the class, and f the fiber. Then if alpha is in L perf, then alpha restricted to f is equal to 0. We can prove that. That's not too difficult. How should we? Yeah. Okay. So by Hodge theory, that's an argument that's pretty much the same as those arguments we've seen in the proof of Matsushita's theorem. So by Hodge theory, suffices to show that the integral over f alpha to the omega n minus 1 is equal to 0, and the integral f alpha squared omega n minus 2 is equal to 0. And here, omega is a Kähler class on X, and as usual, I think of this here as the restriction of this Kähler class to fiber F. So the reason is that if you have this, then alpha is somewhere in the primitive cohomology, and if for such an alpha you have this equation here, well, that's a quadratic form which is supposed to be negative definite on the primitive cohomology. Therefore, if you have something something that vanishes, then it has to be 0. All right. So, the proof of this is, as always, we use the Fujiki relation. So Fujiki relation goes like your Q and alpha plus, and then I introduce two variables, polynomial in two variables, say S times omega plus T times L, raise it to the nth power, gives me the integral over X, alpha plus S times omega plus T times L to the power 2n. Okay. Left-hand side can be simplified, so I think probably maybe I can, I should have said that before. I think I already used it here. So this alpha is supposed to be in H11 without loss of generality, because if it's an H20, then it restricts to 0 anyway, because it's a Lagrangian Fibrations. So the left-hand side can be computed as follows. There is Q of alpha, then there is 2s Q of alpha omega. There is S squared Q of omega, and then there is 2s times T times Q of omega comma L, and then the whole thing to the nth power. Okay. So the reason is that so L is perpendicular to alpha by assumption, and Q of L is 0. And I think that's all. The right-hand side, before I don't want to look at the right-hand side, but now I look at the coefficients. And so what do I want to get? I want to get this expression here. So I look at the coefficients as s to the n minus 1 times t to the n, and s to the n minus 2 times t to the n, and make a comparison of the coefficients. So on the left-hand side, what do I get? Well, how can I get s to the n minus 1 times t to the n? Well, whenever I want to produce a t, I also have to produce an s. So I can actually never get something like that or something like that. So the left-hand side is always 0, and the right-hand side is, oh sorry, I forgot, here of course there is some constant, Fujiki constant, and then there is some other constant, and then we actually get what we want, namely the integral over the fiber of alpha times omega n minus 1, integral over the fiber alpha squared omega n minus 2. Okay, and this is it. The point being again that L to the n is some non-zero multiple of the fiber, and that's how I get from this integral over x to an integral over f. So you see, same arguments as in the Matsushita proof, or it's also proved by Matsushita, and this proves this inclusion. So, corollary is that that x comma f is equal to the Hodge locus of L, and yeah, and that's it. Okay, so that means we get an equality here by Matsushita. It's not completely obvious. Well, I mean, it's obvious from the theorems, but let me point out what we actually need. So what I computed looks like an equality of the tangent spaces of these deformations. Now, if I have two smooth spaces included in one another, and the tangent space of one is equal to the tangent space of the other, then the spaces are equal. So here, let me point out that a priori, these two spaces, there's no inclusion between the two. However, we use that precision in Lagrange's theorem, saying that not only is it smooth of this and that dimension, but it's actually a Hodge locus. It's the Hodge locus of V perp. And what we've shown is that V is equal to L perp. So they're the same in the period domain. All right.
Before you reach that point, you can ask, so does this, does the Voisin theorem shows that the Hodge, the deformation of xy actually equal to deformation of x intersects with projectization v?
Sorry, come again?
Sorry, I mean, to analog to the corollary, does this Voisin theorem also implies that the deformation x comma y is equal to deformation x intersect with v per like v, like PV?
Yes.
Yes, okay, that's true. Yeah.
So if you look at this, diagram, you see it would be sufficient to prove that one remaining inclusion is an equality in order to conclude that everybody is equal. So I'm going to switch to wet.
I just realized that this is, you said there's an L in the notation, and this is an L. I read it as an E or something.
You have problems with my handwriting.
Well, no, it's the American system's fault. They don't emphasize.
Oh, you did not tell me how many inches an L has to be. Okay, but this I'm not going to prove. Yes, that's the difficult part. The theorem by Matsushita. Yeah, but Matsushita says that so that L, the universal line bundle, on curly x over def x comma L. I'm sorry, I mean I denoted curly x to be the universal deformation over def x. Now I use it for the restriction. That's okay. I don't want to switch notation every time. So universal line bundle on curly x. Yeah. Then So the situation is the same as before, right? So on X, I have a Lagrangian fibration. L is the pullback of an ample from the base from this Lagrangian fibration. So then the statement is that for all T in def X, L, and speaking of germs, that means for all T sufficiently close to the origin, the line bundle L T is semi-ample on curly xt. So recall semi-ample tells you that some multiple of this line bundle is base point free and therefore gives a map to some projective space. So the second part is just a direct consequence of the first part. And so the map from curly x to, well, I take the projectivization of, let me call that pi here, pi lower star of L tensor n over def x comma L. Is a Lagrangian fibration onto its image. So it is a family of Lagrangian fibrations. All right, let's have a look at it again. So so this thing here, okay, it's not a direct consequence. I have to show that this actually commutes with base change, but this is part of the theorem of Matsushita. But if I have that, then so xt to projectivization of global sections of LT gives you LT to the n gives you Lagrangian fibration, and this is how it works in families. Okay. Of course, it doesn't say that the base is Pn, right? That's why I say onto its image embedded in some high projective space. Okay, well, and then so this finally the last conclusion here. So this is Matsushita's lemma. And this here, equality here is Matsushita's theorem. And this here is the logical consequence of the other equalities. So all of these spaces coincide and are actually a hypersurface in the universal deformation of X. Which is good because this means that there are almost all problems about Lagrangian fibrations you can actually solve after deformation. The grain of salt, yeah. So problems which are invariant in the deformation. So for example, the existence of Lagrangian fibrations, so given a line bundle with square 0, and which is in the closure of the positive column, say it is Neff. So the SYZ conjecture, suppose you need some, say, Hodge theoretic assumptions on Chicago, whatever. You just go and deform a little bit. You can prove the SYZ conjecture on the deformation, and Matsushita tells you that's fine. And come back. All right.
Similar for some result that you mentioned in the first days, at least when we were discussing whether the first day there were some reduction like X projective or the base projective. Can you first prove these results so that you could always reduce to the projected case and then Fanon is
probably yes, but I think there is an easier way. There are these deformations, look, these generate twistor spaces by Verbitsky. I think you can use them to deform your Lagrangian fibration a little bit. You don't need to deform it over the whole place, and then you just use that whenever you have a non-trivial family of IHSMs, then projective guys are dense. You just need one deformation. I think you can get this.
But you need to know also that the Lagrangian fibration deform.
I think in Verbitsky's argument, we don't consequence.
You may have taken a twistor direction that goes away from the deformation of X and L. So you don't.
No, it's not a twistor space. It's what he calls a degenerate twistor space. So it's not a positive free space, but a semi-positive thing. You pull back so it's essentially you change the class sigma, the period sigma by sigma plus t times L, where L is the class of the pullback of the line bundle.
Oh, okay, so you remain inside the locket.
Exactly. Okay, yeah, so that's nice. But here's a corollary. Actually, not of the theorem, but of Matsushita's lemma already. Says that if so, in the above situation, if I want to keep the notation from the beginning. If I take the restriction map from H2 of X to H2 of the general fiber of the Lagrangian fibration, take the rank of it. Well, what's the rank? I mean, if the kernel of that is equal to L per codimension 1, then kernel plus image means that this has to have rank 1. Okay. So F has a canonical polarization. That's pretty nice. So we've argued. So in the proof of projectivity of the general fiber, we have taken a suitable Kähler class that was not rational on the whole space, integral, say, but its restriction on the fiber turned out to be integral and therefore gave an ample line bundle. But a priori, there could be many ways to do that. So take a different Kähler class, you get a different line bundle. But here the statement is, whatever Kähler class you take, you just get a multiple of that. Right? And so if you look at the image of the Kähler cone, this is a ray. It's just a ray in H11 of F. And this ray is integral, and therefore it has a minimal generator. And this is a canonical polarization. So not only are the fibers abelian varieties, but they are polarized in a canonical way. So here is a problem I'd like to propose to all of you, or whoever is interested, compute. So compute this polarization for O'Grady 6 and O'Grady 10 deformation type, or singular examples. Singular examples such as the Nikunin orbit folds. So what I haven't told you, but which is actually not difficult to prove, is, well, these things have a canonical polarization, but also if you deform the fibration, the polarization type does not change. So for example, for K3M type, it's principal polarization, and it doesn't change. So it's the same over the whole component of the moduli space of pairs x, L. And it has been computed, so Lehn computed the K3n and cum-n type polarizations. So Lehn was a PhD student of Klaus Hulek, and I proposed his PhD topic, which was to compute this polarization. Actually, I asked him to show that it's the same for, I mean, there's only one polarization type for K3n and one polarization type for cum-n. I think his result was that K3n is true, and for cum-n, I think there are two different polarization types. And for this, he needed some results about the monodromy, which I think at the time have not been known for the O'Grady examples. So I think now one should be able to compute the polarization types that arise for 6 and OP10, at least in principle, and maybe also for singular examples. And I think that would be interesting. Well, here's a possible application of that. You could try to construct new examples of IHSMs by constructing a Lagrangian fibration. So if we know all the possible, all the possible polarization types that show up on the fibers, you construct an example out of a new polarization type, then you have a new example.
Sorry, but it doesn't depend the problem and even the result of
it does not depend on polarization. On deformations. So if you have your Lagrangian fibration and you deform it, you remain with the same polarization type. It could be that there are several components of the moduli space of varieties X together with the Lagrangian fibration. I don't remember whether there are, but for example, in the Hilbert scheme case, they all have the same polarization type. You need to check it for like one element per component of the moduli space. That's what he did.
I have the impression that the Onjong has some result in this direction, for grade 6 or grade 10.
Oh.
But for Kummer type, I think that it depends on the divisibility of n. That there were only.
Yeah, for Kummer type, it was not always the same polarization. There were more than one type showing up.
But more than one. More than two.
What?
More than two.
Maybe. I don't remember. Well, I suggested, Benjamin, that there were, and to prove that there is only one, but then we came up with several, and yeah, more than one, definitely.
So the name was Wiener?
Wienek. W-I-E. Yeah, okay, this time you're right. I mean, that's bad handwriting. Okay, so here's another application. And it's the following. So same notation as as above. Or maybe let me recall that because I have to introduce some additional notation. So I have f from x to b. I have e circ, x circ, and f circ. And this is the locus in B over which f is smooth. So this here is supposed to be a smooth morphism. Take the open in B over which this is true, and maximal open over which this is true. And then there is this lemma by, well, it's Voisin, but the version I give is taken from Baker, and says that the R local system V1, that's R1 F circ lower star of R X circ. Okay, maybe I shouldn't have called it a local system. Is irreducible as, well, okay, no, let me not create any confusion. The R, polarized R variation of Hodge structure. Polarized R variation of Hodge structures. V1, this thing here, is irreducible as a polarized R variation of Hodge structure. Right, so, I mean, that's a local system, but it carries more structure, and with this, I mean, in the category of polarized R VHS, it is irreducible. And it's actually an easy consequence of Matsushita again. So let's prove it. Suppose not. Then V1 is a U plus W, and both of them are real variations of Hodge structures, polarized. So then the polarizations of U and W, there are two polarizations, give classes in H0, what do I need? H0, so R2 F circ lower star R X circ, which is H0. So because we speak about vibrations in abelian varieties, the second cohomology of an abelian variety is the wedge 2 of the first cohomology. So this is H0, so the same holds true for these local systems. Lambda 2 of V1. And this, now you can decompose it as the H0 of lambda 2 of U plus the H0 lambda 2 of W plus the H0 of U tensor W, and the polarizations, so pole 1, pole 2, give you classes in here. But now, so by the invariant cycle theorem, these classes come from the cohomology of the total space, from H2 X R. Yeah, that's a contradiction. To the rank of H2X to H2F being equal to 1. Yeah. You definitely have two classes coming from the polarizations, but there can only be one class. Okay.
Sorry, Christine, I didn't get what this bold R with respect to.
R just means the real numbers, and that's the locally constant sheet.
Okay.
Yeah. So fiber-wise, so that's a local system with fiber, the homology with real coefficients.
Does it matter in whether you use the real coefficient and not another C?
Yeah, let me comment on that. Somehow it depends from which direction you're looking at it. So in the proof, I could have used any other extension of Q, because the only thing I needed was that the rank of the restriction map to the fiber. There was so there. By universal coefficients, once you have it for Q, you have it for all extensions of Q, so that's fine. But if you think about it, R is maybe the strongest assumption that you could put, because so think of variations of Hodge structures over a point. Variation of Hodge structures over a point so over Q, an irreducible variation of Hodge, polarized variation of Hodge structure can be arbitrarily big. The dimension of the underlying vector space can be very big. Whereas over the reals, for wave 1 Hodge structures, take a class in H10, take its complex conjugate in H01, so they generate a real vector space, and that's an R sub-Hodge structure. So being irreducible for a real Hodge structure is a much stronger statement than for a Q Hodge structure. And same for variations. All right. And this is one of the main ingredients in Baker's proof of the Matsushita conjecture. All right. We'll see in the Matsushita conjecture.
The smooth scale.
Oh, doesn't matter. So the conjecture, the conjecture now theorem is if you have F X to be the Lagrangian fibration of an irreducible holomorphic symplectic manifold X, then there are just two possibilities. Either F is isotrivial, or F is of maximal variation.
Not F0,
Sorry?
not F0,
Or, I mean, call F isotrivial. Yeah. Sure. Okay. So I think that's an important theorem, an important conjecture before, and this is, for example, used in proof of Lehn and Tosati, proof of Wang's theorem. And probably, yeah, I think also in the Baker-Schnell proof of the theorem. Okay, are you familiar with the notions of isotrivial and maximal variation? Okay, then it's a good idea to explain it. So I think isotrivial, all smooth fibers are isomorphic. All smooth fibers, and that's I think one way of defining it. You can then show, I think, that after a finite base change, you actually get something that's birational to a product, at least if the space X is projected. So it means instead of infinitely many abelian varieties, there's actually only one, and that is repeated in every smooth fiber. So, for example, you take E in an elliptic curve, and you take E cross E. You take the quotient by plus minus 1, and then you project the E modulo plus minus 1. That is, of course, P1. And here you take the resolution, which is the Kummer surface of E cross E. And that is an isotrivial fibration of a K3 surface with a smooth fiber E. So there's only this E, that's an isotrivial thing. And of course, take the Hilbert scheme of that, or take similar constructions to get an isotrivial vibration of this format. So that is always possible. I don't know of an explicit construction on the O'Grady's, but probably people know. Yeah, maximal variation is the opposite. So there are as many as possible moduli of abelian varieties in your Lagrangian fibration. Okay. So now, so maximal variation is this. If you have so x0 over e0, then hope to not say anything, even though you should get a map from here to the moduli space of abelian varieties, an together with some polarization. So I mean, So you certainly get a classifying map on the level of Hodge structures as soon as you go to the universal cover here, you get one in the period domain. And I think you can get this just by composing with the quotient map, and I think it should tend to be. I'm not 100% sure, but otherwise do it on the universal cover. So you have this phi here, and you want that the dimension of phi is equal to, the dimension of the image of phi is equal to n. That would be maximum variation. And so in principle, the number of moduli of your Lagrangian fibration could vary between 0 and n. But the statement is Matsushita's conjecture, Baker's theorem, is that you can only take the extremal values, either 0 or n. Maybe I should add that, well, it's not proven, but I think what should be true is that the isotrivial case is the special case, and numerically it should be a maximal variation. So I think Ben even told me that he can prove that if he has some additional assumption on the betting.
Yeah, with additional assumption on what? Please repeat the last sentence.
Yeah, so apparently you can prove that not all Lagrangian fibrations in the moduli space can be isotrivial if you put some assumption on the second Betti number of x. So an isotrivial can always deform to one of maximal variation. I forget what the exact number is.
Is having maximal variation kind of an open condition? It is not.
That's a good question.
I think it's the result that you mentioned. No? I know you may have a wall divisor. Wait, right? No, you said that you can always deform isotrivial to maximal variation.
You can always deform isotrivial to maximal variation. I would guess that maximal variation is an open.
Yeah, isotrivial. I mean, it's like saying that the map to the moduli space of a million varieties has positive fibers, which is a closed condition. I mean, fiber of positive.
Which is yeah, that's true. You only have that map on the smooth locus, but I think you can still use the simple continuity of the fiber. I think that's true.
Thank you.
Okay.
The opposite, that it's open. Whereas if you can always, in the deformation class, you could always deform to something that is isotrivial.
That's not clear. I would like to see that this is true.
Because I think is one of the strategies to classify isotrivial. I mean, if you could always reduce to an isotrivial one.
Yeah, it would be nice. So that's a remark. So open questions, conjectures in the isotrivial case. I don't know whether it gets any easier, but at least you could try. So all the questions and conjectures I posed, asking the additional assumption that writing the fibration be isotrivial is certainly a reasonable assumption, would already lead to a nice result. And over time, I